Metals can be super dangerous, both to our oil and to us as humans. If you've ever heard of the term heavy metal poisoning, you'll know that if we as humans consume metals in excess, or types of metals that we're not really supposed to, that can lead to poisoning and eventually death. Well, the same kind of thing happens to our oil. Metals that are suspended or dissolved in the oil can promote the oxidation process and can be extremely harmful. So we have to use special additives called metal deactivators that helps make them inert. Want to find out more? Let's look at it. Let's talk about metal deactivators. Now, within the family of corrosion inhibitor additives, there are basically two different types of families. You've got the surface passivators and the chelators. Now, surface passivators are things like mercaptobenzothiazole. We've heard about this in previous videos, and effectively what they do is they act like a surfactant or a detergent or something like that. So they want to adhere to the surface of the metal and form an inert barrier that prevents the oil and the metal from coming into physical contact with each other. So if there's no physical contact, then there's no chemical reaction between the two. And this is how surface passivators prevent metals from interacting with the oil. There are a second kind, which are called chelators. And an example of this, I'm going to butcher the name here, is called disalicylidene diaminopropane. All right, you may have already been familiar with the term chelation. So chelation therapy is something that is done when someone has been poisoned, for example. We want to introduce a chelating agent into their blood, which is going to bind with the poison and prevent it from interacting in a negative way. Effectively, what we're doing is we are looking in the bloodstream for heavy metals, right? These heavy metals are traveling through the blood and can get into all your vessels and cause a lot of damage to your cells. And so what we effectively want is a type of molecule, which I'm showing here in yellow, which is going to attach itself to the metal ions to prevent them from doing any kind of damage. That's what we want. So that's what chelation therapy is in humans. And chelators as additives are effectively chelation therapy for oils. So first of all, we might want to ask ourselves, why is it that metals are so bad for both humans and for oils? The answer has got to do with oxidation states. So things like iron and copper are extremely familiar to us, and they are very common in machine applications. So iron usually comes in the form of some kind of steel, and of course copper is very common in things like coolers. Now the problem with iron and copper is that they can exist in many different states within our oil. So for example, maybe we have wear metals, and so these are actual pieces of metal, that is iron or copper or zinc or something like that, or tin, and they are particles that are traveling inside the oil. Now, first of all, they can do damage from a abrasion standpoint, right? But they can also do damage because they can accelerate the oxidation process. The main reason for this is that metals form ions, right? So you'll be familiar with, let's say, iron 2 plus and copper 2 plus, but especially within the transition metals, and that's that sort of group in the middle of the periodic table, these metals can form ions of different charges. So iron, for example, can form, that is IRON, can form 3 plus ions, and copper can form 1 plus ions. Now these ions represent different oxidation states, and in some reactions, what they do is they lower the energy barrier by changing from one oxidation state to another. So it's almost like if you can think of someone trying to do the pole vault, right? There's a certain amount of energy that you need to overcome in order to get the reaction to occur. And what these metals do is they help you cheat. They help lower the bar so you don't require as much energy. So while they change state, they're not actually consumed in the process. And that makes them a little bit like a catalyst. So sometimes we use catalysts to promote a reaction that we want to occur. But in this instance, these are having catalytic activities that we don't desire. So how on earth do we get around this? One thing that we could do is come up with some kind of molecule that would bind to the metal and form a salt. So if you'll remember, acid plus base equals salt plus water. Why wouldn't we want that? Well, the problem with salts in oil is that they tend to precipitate out, right? So they'll form particles that will then fall out of solution. They'll do things like, block your filters, they'll consume additives. In general, we don't like precipitation of additives or of metal salts, right? So what we want is a molecule that can bind with the metal, and that's going to form, in chemistry terms, it's called a complex ion, right? So that means that it's not going to fall out of solution. And if you're familiar with biology, then you'll recognize this molecule as being ethylene diamine, which is a very common ligand that forms a complex ion with metals. Do I need to know this terminology? No. Effectively, what you need to know is that chelating ligands are those that can form multiple interactions with a metal. The reason why that's important is because this isn't necessarily a bond in the traditional sense, right? What we want is a stabilizing reaction with the metal ion. And what we want is a circumstance in which if the bond with one of those nitrogens is lost, then the other nitrogen is still hanging on to that metal until such a time as the bond with the other nitrogen regains itself. So there's kind of a probability of whether the bond is maintained, and it makes it very rare that both of those nitrogens lose the bond at the same time. Now, this particular molecule is not actually a chelating ligand in most oils because it's not necessarily fit for purpose, but it gives you an idea for the kind of shape that most of our chelating additives should have. And sure enough, if you'll remember the molecule that we showed at the very beginning, which was this disalicylidene diaminopropane, I think I did it better this time, that has a very, very similar shape. You can see that the two nitrogens are going to be able to bond with that metal ion and form a complex ion.